The sun may look calm from Earth, but it is a powerful and unpredictable star. Every second, it hurls streams of charged particles called the solar wind into space. Most of the time this flow is steady, but sometimes the sun erupts violently, releasing massive bursts of energy known as solar flares and coronal mass ejections. These explosions launch billions of tons of plasma into space at speeds of over 1,000,000 miles per hour, and when they are aimed at Earth, they can change the space environment around our planet in dramatic ways. When these charged particles collide with Earth's magnetic field, they distort it and inject energy into the upper atmosphere, creating what scientists call space weather. The most beautiful result of this interaction is the aurora, shimmering curtains of green, red, and violet light dancing across the polar skies. But these same storms that paint the heavens can also disrupt satellites, interfere with GPS navigation, and even cause large-scale power outages on Earth. During powerful geomagnetic storms, electrical currents can surge through transmission lines, damaging transformers and communication systems across entire continents. To protect our technology and astronauts, scientists constantly monitor the sun. Spacecraft like NASA's Solar Dynamics Observatory and the upcoming SWFOL-1 mission orbit between Earth and the Sun, tracking solar flares and measuring the speed and density of the solar wind. Together with ground-based observatories, they create early warning systems that allow engineers to safeguard satellites, adjust spacecraft operations, and reduce the risks of radiation exposure to astronauts. Space weather reminds us that we live within the sun's reach, inside a vast magnetic field that connects our planet to its star. Understanding how solar storms work not only helps us protect modern technology, but also teaches us how stars interact with the worlds around them. As we send more spacecraft and astronauts deeper into space, learning to predict and withstand the sun's temper will be essential for the future of exploration. Even 150 million kilometers away, the sun continues to shape life and activity here on Earth. True or false, space weather originates from the Earth's magnetic field. False, space weather begins with activity on the sun, such as solar flares and coronal mass ejections that send charged particles into space. What are the main sources of space weather? Solar flares and coronal mass ejections. Fill in the blank. The stream of charged particles flowing from the sun is called the blank wind. Solar wind. Fill in the blank. The mysterious lunar horizon, blank, was one of LADE's investigation targets. A coronal mass ejection. What natural phenomenon on Earth is a visible result of space weather? Auroras. If charged particles from a solar flare travel at 1,200 kilometers per second, how long will it take them to reach Earth, which is about 150 million kilometers away? To find how long solar particles take to reach Earth, divide the distance by their speed. 150 million kilometers divided by 1200 gives 125,000 seconds. Converting to hours, that's about 35 hours, roughly a day and a half for a solar storm to arrive after a major flare. True or false, auroras are caused by charged particles colliding with atoms in Earth's upper atmosphere. True. Fill in the blank. The region around Earth affected by its magnetic field is the blank. Magnetosphere. Which spacecraft helps monitor the Sun for space weather prediction? Solar Dynamics Observatory. Fill in the blank. Satellites like the Solar Dynamics Observatory help scientists blank solar activity. Monitor. True or false, a powerful geomagnetic storm can disrupt GPS and power grids on Earth. True. If a burst of solar wind travels for 20 hours at 800 kilometers per second, how far does it go? To calculate distance, multiply speed by time. 800 kilometers per second times 72,000 seconds gives 57.6 million kilometers. That's about 1/3 of the distance from the Sun to Earth, showing how fast solar wind can spread through space. During a major solar storm, which of the following is most at risk? Satellites and power grids. Fill in the blank. The Carrington event of 1859 was the most powerful, blank, storm ever recorded. Geomagnetic. If charged particles from a CME took 40 hours to reach Earth, traveling 150 million kilometers, what was their average speed? To find the speed, divide distance by time. 150 million kilometers divided by 144,000 seconds equals about 1,040 kilometers per second. That means the particles from this coronal mass ejection raced through space faster than 1,000,000 kilometers every 1,000 seconds. A reminder of just how powerful the sun can be. How did you do? Tell us in the comments below. And thanks for watching Brainy Kids. We hope you had fun today. Like, subscribe, and hit the bell so you never miss a quiz. See you next time, Brainy friends.